Some of the universe's most colossal stars are hiding truly bizarre secrets. We are about to journey through 30 of their strangest behaviors, each one a cosmic puzzle that defies our current laws of physics. You will discover how these stellar giants can vanish without a trace, pulse with the energy of entire galaxies, and even tear themselves apart from the inside out. How can a star shine with a light so intense it should destroy itself, yet somehow survive? What mysterious force can fling a star across the cosmos at unimaginable speeds? By the end of this exploration, you will see the universe's most powerful engines in a completely new light. What do you believe is the ultimate fate of a star that breaks all the rules? Our journey into the strange begins with a star that is essentially tearing its own skin off. Picture a star so massive and unstable that it cannot hold onto its own body. This is runaway mass loss, a violent tantrum on a cosmic scale. While all stars shed some material through stellar winds, a gentle breeze of particles, these supermassive stars experience something entirely different. They erupt in colossal outbursts, hurling entire oceans of solar material into the void. We are not talking about a steady stream, but a sudden, catastrophic expulsion. In a single event, a star can eject more mass than our own sun contains over its entire lifetime. Imagine a mountain range the size of the Himalayas being blasted into space every second. This is the ferocious reality for these stellar behemoths. The star does not just lose weight, it undergoes a dramatic transformation. Its outer layers, the very regions that define its size and brilliance, are violently stripped away. This process completely rewrites the star's future. A star destined to die as a supernova might instead be whittled down into a quieter, less dramatic corpse. What triggers such a self-destructive frenzy? The internal pressures become so immense that the radiation pushing outward simply overpowers the gravity holding the star together. The star's own light becomes a weapon that blows its surface apart. This is a star fighting a desperate and ultimately losing battle against itself. This internal battle can become so violent that the star itself is thrown from its home. Far from being static ornaments, some supermassive stars are cosmic fugitives, racing through the emptiness between galaxies at millions of miles per hour. These are hypervelocity ejections, and the forces required to achieve such speeds are almost beyond comprehension. The most common scenario involves a stellar dance that turns deadly. Picture a binary system, two stars locked in a tight gravitational embrace, orbiting a supermassive black hole at the heart of their galaxy. If one of those stars is pulled into the black hole and consumed, the other can be slingshotted away with unimaginable force, like a stone from a giant sling. The surviving star is flung out, carrying the entire energy of its partner's destruction as pure, unstoppable momentum. Another pathway is through the kick from a supernova explosion in a binary pair. When a star dies in this asymmetrical blast, the recoil can literally punt its companion star out into the void. These are not gentle nudges, they are gravitational cannon shots. The ejected star becomes a lonely traveler on a one-way trip into nothingness, a blazing runaway from the cosmic community that created it. What does this mean for the star itself? It is condemned to a solitary existence, burning through its fuel far from any galactic nursery, destined to end its life alone in the intergalactic dark. These stellar outcasts are not the only ones with violent inner lives. Deep within another class of supermassive stars, a different kind of power is being forged, one that twists the very fabric of space around it. We are entering the realm of the magnetic field monsters. Our own sun possesses a magnetic field, one that creates beautiful auroras and occasional solar flares. But the fields surrounding these stellar giants are something else entirely. They are not merely strong, they are almost unreal, measuring trillions of times more powerful than the sun's. To grasp this scale, imagine a common refrigerator magnet. Now, envision a magnet so potent it could pull a battleship from 1,000 miles away, not with a gentle tug, but with a force that would rip it to shreds instantly. That is the level of ferocious power contained within these stars. This unimaginable magnetic force does not lie dormant. It actively strangles the star, creating colossal starquakes that ripple across its surface. These are not like the tremors we experience on Earth. A single starquake can release more energy than our Sun will emit over 10,000 years, cracking the star's crust and unleashing firestorms of radiation. This magnetic grip also directly influences the star's violent weight loss, channeling and accelerating the ejected material into focused, deadly beams. But the most dramatic display of this power is the radiation these fields generate. They act as natural particle accelerators, whipping charged particles to velocities approaching the speed of light. When these particles collide with the star's own matter, they erupt in the most energetic light in the universe, intense blasts of X-rays and gamma rays. A single flash from one of these magnetic monsters can outshine an entire galaxy in high-energy radiation, a brief, terrifying scream of power across the cosmos. What kind of star can survive such internal turmoil, where its own magnetic heart is trying to tear it asunder? That magnetic turmoil is a gentle hum compared to the internal chaos of a star tearing itself to pieces over and over again. We now encounter pulsational pair-instability, a process so violent it turns a star's final death into a series of rehearsals. Deep within a supermassive star, the core is an inferno of unimaginable heat and pressure. Under normal conditions, this furnace is stable, fusing elements and pushing outward against the crushing weight of the star's outer layers. But for the most massive stars, something bizarre happens. The core becomes so incredibly hot that the radiation inside it is no longer just light, it is pure energy. This energy is so concentrated it spontaneously transforms into particles of matter and their mirror opposites antimatter. This is not science fiction. The star is literally creating electron and positron pairs out of raw energy. The problem is when a particle of matter meets its antimatter twin, they annihilate each other in a flash of pure energy. This creation and destruction seems balanced, but it has a catastrophic effect on the star's core. That process of pair production effectively steals the radiation pressure that was holding the core up. It is like suddenly removing the supporting pillars from a colossal building. Without that outward push, gravity wins instantly. The core begins a catastrophic collapse. This is where the pulsation begins. The collapse is so violent and heats the core so intensely that it triggers a runaway thermonuclear explosion. This is not the full supernova, not yet. It is a partial eruption, a single, monstrous pulse that blows the star's outer layers into space with the force of a small supernova. The star survives, but it is grievously wounded, its outer envelope torn away. The explosion relieves the pressure and the core stabilizes, only to begin heating up once more. If the star is still massive enough, the entire horrific cycle repeats. The core heats up, creates matter and antimatter, loses pressure and collapses again, triggering another pulse. A single star might experience 3, 4, or even 5 of these violent eruptions over thousands of years, each time blasting a sun's worth of material into the cosmos. It is a stellar body convulsing, caught in a cycle of self-destruction and temporary recovery. What remains after the final, feeble pulse is a star that has been stripped down to its essence, a bizarrely shrunken object with a story of repeated cosmic violence written into its very atoms. This self-destructive pulsing finds its ultimate expression in a class of stars known as luminous blue variables. These are not just unstable stars, they are stellar celebrities prone to spectacular public meltdowns. They exist on a razor's edge, hovering at the very theoretical limit of how massive a star can possibly be. Their immense size and luminosity create an internal pressure cooker that periodically becomes too much to contain. The result is not a quiet shedding of mass, but a grand, explosive performance. A luminous blue variable can, in a single outburst, eject a shell of gas equal to the mass of several of our suns. This is not a gentle stellar wind, it is a volcanic eruption on a cosmic scale. For a brief, dazzling period, the star can become so bright it outshines entire galaxies, its brilliance increasing by a factor of 100 or even 1,000. These eruptions are so violent and luminous that astronomers observing them from afar have sometimes mistaken them for actual supernova explosions, the final death throes of a star. But then, something remarkable happens. The star does not die. The eruption subsides, the ejected gas forms a vast, glowing nebula around the star, and the luminous blue variable returns to a quieter state, only to build up pressure and do it all over again centuries or millennia later. It is a star repeatedly faking its own death, surviving cataclysms that should spell its end. What kind of internal chaos allows a star to endure such violent, cyclical rebirth? Even after surviving such violent pulsations, the chaos around a supermassive star can take on a bizarre rhythm of its own. Deep within the swirling vortex of its own dismembered material, some of these stars exhibit quasi-periodic eruptions. Picture the vast disk of superheated gas and dust that often surrounds these giants, a whirlpool of matter slowly spiraling inward. Within this accretion disk, something strange occurs. At seemingly regular but not perfectly clockwork intervals, a colossal burst of energy is unleashed. These are not the random flickers of a restless star, nor are they the precise ticking of a cosmic metronome. They are immense, repeating explosions that flare up, fade, and then flare up again on a rough schedule. Each eruption can release more energy than our sun will produce over 1 million years, all concentrated into a brief, dazzling flash. What could possibly cause such a powerful and repetitive event? The leading theory points to a gravitational dance of death within the disk itself. Imagine a smaller, dense object, perhaps the remnant core of a star that was torn apart, orbiting through the dense gas of the accretion disk. Every time this object plunges through the densest part of the disk on its elliptical path, it creates a massive shock wave. The resulting friction and compression heat the gas to incredible temperatures, triggering a runaway thermonuclear reaction. It is like a celestial engine misfiring on a grand scale, with each pass of the orbiting object lighting a new fuse. Another possibility involves instabilities within the disk's own magnetic fields, which build up stress until they snap, releasing their pent-up energy in a predictable cycle. The quasi-periodic nature of these eruptions, their almost but not quite regularity, is a key clue. It tells us we are not looking at a simple mechanical process, but at a complex, chaotic system that is struggling to find a rhythm. These eruptions are the star's final, rhythmic death throes, a coded message written in fire that we are only just beginning to understand. What other secrets might be hidden within the timing of these cosmic heartbeats? This defiance of self-destruction reaches a fever pitch with stars that laugh in the face of a fundamental cosmic law. They shine with a brilliance so intense it should tear them to pieces, a phenomenon known as Super-Eddington luminosity. The Eddington limit is a cornerstone of astrophysics, a calculated line in the sand. It represents the maximum brightness a star can achieve before the outward pressure of its own radiation overpowers the inward pull of its gravity. Exceed this limit, and the star's light should act like a hurricane, violently stripping away its outer layers until it is no longer a coherent object. It is a law of physics that says this bright and no brighter. Yet we observe stars that do not merely approach this line, they blaze straight past it. They are shining with a ferocity that, by all our understanding, is impossible. They are cosmic rebels breaking the most basic rule of stellar existence. How can they possibly hold themselves together? The answer may lie in the very chaos they create. When a star pushes past the Eddington limit, its outer layers do not simply fly off in a smooth, steady stream. Instead, they become a turbulent, frothing sea of plasma. This chaos might actually be the star's salvation. Dense, cooler clumps of gas can form within this maelstrom like rocks in a raging river. These clumps are partially shielded from the intense radiation, and their collective weight and complexity could provide just enough temporary stability for the star to avoid immediate disintegration. It is not a clean, stable balance, but a messy, violent, and temporary compromise. The star is constantly on the verge of blowing itself apart, held together by the very turbulence its own light creates. Another possibility involves the geometry of the star's magnetic fields, which might channel the escaping radiation into powerful jets at the poles, funneling the destructive force away from the rest of the stellar surface. This allows the star to appear stable overall, even while it is venting its excess energy in focused, ultra-luminous beams. Observing these stars forces us to reconsider the very definitions of stability. They are not serene, balanced orbs, but frantic, churning engines barely containing their own power, showing us that sometimes chaos is the only thing preventing total collapse. What other fundamental laws might these stellar giants be bending in their violent struggle to exist? The chaos of one star's struggle for existence can spell doom for its closest neighbor. Binary system cannibalism reveals a stellar relationship turned predatory, where two stars locked in a gravitational embrace engage in a one-sided feast. Most binary systems are stable partnerships with both stars orbiting a shared center of gravity. But when one of those stars is a supermassive giant, the balance of power is shattered. The immense gravity of the larger star begins to pull material directly from the atmosphere of its smaller companion. A relentless river of hydrogen and helium flows across the space between them, siphoning the very lifeblood from one star to fuel the other. This is not a gentle transfer. The stolen gas pulled from the donor star spirals down onto the surface of the supermassive star or forms a seething, superheated disk around it. With this constant influx of fresh fuel, the cannibal star can burn brighter and longer than it ever could alone, its mass and luminosity swelling from its partner's sacrifice. The consequences for the donor star are devastating. It is progressively stripped down layer by layer until only its dense, exposed core remains a stellar corpse orbiting the star that consumed it. Sometimes the process goes even further. In an ultimate act of cosmic consumption, the supermassive star can drag its companion's core inward until the two objects actually merge. This collision creates one of the most exotic and theoretical objects in the universe, a Thorn-Zitkau object. Picture a red supergiant star, but with a secret hidden deep in its heart. Instead of a fusion-powered core, it contains the entire collapsed remnant of a neutron star. This bizarre hybrid object would shine with a strange light, its outer layers powered by the immense heat radiating from the neutron star core within. Its very atmosphere would be polluted with unusual elements, the telltale signature of a stellar cannibal that has swallowed its prey whole. The feast can also end with a far more violent finale. The constant dumping of fresh hydrogen onto the surface of the supermassive star can trigger a runaway fusion reaction. This isn't a slow, steady burn. It is a titanic thermonuclear bomb igniting on the star's surface, a cataclysm so powerful it can outshine a galaxy for a few incredible weeks. This is a classical nova, and in extreme cases, it can escalate into a supernova that utterly destroys the entire system. The supermassive star, having gorged itself on its companion, reaches a critical mass and explodes, its death triggered by the very act of consumption. What begins as a slow siphon ends in a blaze of self-annihilation, a final, fiery testament to the dangers of getting too close to a cosmic giant. A star's light can sometimes flicker with a warning we cannot yet understand. This is the unsettling mystery of unpredictable dimming, a phenomenon that turns familiar celestial giants into cosmic question marks. The red supergiant Betelgeuse, a brilliant shoulder in the constellation Orion, gave us a masterclass in this behavior not long ago. Over a matter of months, its light visibly faded. To observers on Earth, the star grew noticeably dim, losing nearly 2/3 of its normal brilliance. For a star of that size and prominence, such a dramatic drop was unprecedented. It sparked an immediate and intense debate among astronomers. Was this the final signal, the telltale sign of a core collapse about to culminate in a supernova explosion visible from Earth in broad daylight? Or were we witnessing something else entirely, a more complex and less understood process? The eventual explanation proved just as strange as the dimming itself. The star had not simply cooled or died. Instead, Betelgeuse had likely undergone a massive outburst, ejecting a colossal plume of superheated gas. As this material moved away from the star, it cooled and condensed into an enormous cloud of obscuring dust, a cosmic veil that temporarily blocked a vast portion of its light from our view. This was not a star dying, but a star literally shrouded in its own expelled atmosphere. The implications are profound. We can no longer assume that a star fading from sight is a reliable sign of its impending death. The mechanics of these supermassive stars are so violent and active that they can manufacture their own eclipses. They create temporary curtains of cosmic soot, casting themselves into shadow for reasons we are only beginning to grasp. This forces us to reconsider every flicker we see in the night sky. Is it a final gasp or merely a stellar giant clearing its throat? The next time a familiar star begins to fade, we will be watching, knowing its dimming light could mean anything at all. These cosmic giants can forge a weapon of ultimate destruction in their final moments. A select group of supermassive stars are the confirmed progenitors of long-duration gamma-ray bursts, events that unleash more energy in a few seconds than our Sun will over its entire 10 billion-year lifetime. These are the most powerful explosions we have observed since the universe itself began. But not every massive star earns this cataclysmic send-off. The recipe requires two very specific and rare ingredients. The star must be spinning at a ferocious speed, and it must be metal-poor. In astronomy, metals are any element heavier than hydrogen or helium, the ash from previous generations of stars. A metal-poor star is a relic from the early universe, composed of mostly pristine primordial gas. This lack of heavier elements allows the star to hold itself together more tightly, retaining its mass and its crucial rapid spin throughout its short life. As this kind of star reaches the end of its life, its core collapses to form a black hole. But this is not a quiet collapse. The star's immense rotational energy is suddenly focused, funneling into two narrow, ultra-relativistic jets that scream outward from its poles at over 99.99% of the speed of light. These jets are the gamma-ray burst itself. They are like cosmic blowtorches drilling their way out through the star's outer layers. If one of those jets is pointed directly at Earth, our telescopes can detect the fleeting, blinding flash of gamma rays from billions of light years away. For that brief moment, the dying star outshines every star, every galaxy, every other source of light in the observable universe combined. The sheer violence of this event is difficult to overstate. It is the birth scream of a black hole, powered by the final, frantic spin of a stellar giant. What does it mean for a star to be so perfectly tuned for annihilation, to die in a flash that can be seen across the cosmos? One of the strangest and most violent transformations a star can undergo leads to the creation of a Wolf-Rayet star. These are not stars in their prime, but stellar corpses in the making, blazing with a ferocious intensity that signals their impending doom. Imagine a supermassive star that has been completely flayed alive, its vast, puffy envelope of hydrogen violently stripped away by its own incredible power. What remains is an exposed, searingly hot core, a stellar heart beating in the open vacuum of space. This exposed core is the Wolf-Rayet star, and it is effectively a star turned inside out. Its surface temperatures are so extreme they can reach over 200,000 degrees Fahrenheit, making our Sun seem like a cool ember in comparison. This incredible heat fuels one of its most defining features, a stellar wind of unimaginable ferocity. While our Sun emits a gentle solar breeze, a Wolf-Rayet star unleashes a perpetual hurricane. It hurls its own material into space at speeds approaching 10 million miles per hour, shedding an entire Earth's worth of mass every few thousand years. This is not just a wind, it is a constant supersonic exhalation of the star's very essence. The composition of this wind is what truly marks these stars as alien. With their hydrogen envelope gone, the winds are not made of simple hydrogen. They are composed of the star's own nuclear ash, a bizarre cocktail of helium, carbon, nitrogen, and oxygen that has been fused deep in its core and is now being blasted directly into the cosmos. A Wolf-Rayet star is quite literally polluting the galaxy with the building blocks of future planets and life, all while screaming its own death warrant across the light years. This strange chemistry creates a spectacular visual signature, with the star often shrouded in a glowing, clumpy nebula of its own ejected material, a cosmic funeral shroud being woven in real time. But what is the ultimate fate of such a bizarre object? Their exposed, massive cores are ticking time bombs. Many astronomers believe that the most massive Wolf-Rayet stars are the direct precursors to the most violent explosions in the universe, long-duration gamma-ray bursts. Their rapid rotation and lack of a hydrogen envelope create the perfect conditions for the formation of those planet-vaporizing jets when the core finally collapses into a black hole. Even if they do not produce a gamma-ray burst, their destiny is almost certainly a spectacular supernova. The very process of shedding their outer layers has sealed their fate, leaving behind a core that is primed for a catastrophic collapse. A Wolf-Rayet star is a final, brilliant, and terrifying phase of stellar life, a star that has already torn off its own skin and is now burning down to its inevitable explosive end. What does it mean for a star to spend its final millennia as a bare, raging core, screaming its composition into the void? Some stars do not dim with the gentle grace of a setting sun. They vanish. A star that shone brightly for years, a fixed point in the sky, can suddenly drop into near invisibility over a matter of weeks. This is the bizarre signature of an Coronae Borealis variable, a star that plays a cruel game of cosmic peek-a-boo. These are not ordinary supergiants. They are carbon-rich, meaning their atmospheres are overflowing with the element of soot and diamonds. Under normal conditions, this carbon exists as a superheated gas, transparent to the star's fierce light. But when conditions are just right, or perhaps just wrong, the atmosphere cools slightly at a certain altitude. It is a subtle shift, but for carbon, it is a trigger. The gas begins to condense, not into water droplets like in our own clouds, but into solid particles of pure carbon. Imagine a cloud of microscopic graphite, a fog of cosmic soot, suddenly blooming in the star's upper atmosphere. This cloud is not wispy or thin. It is an opaque, light-blocking shroud that forms directly in our line of sight. The star's brilliant light is abruptly choked off, and from our perspective, it simply fades away, sometimes becoming hundreds of times dimmer. The mystery deepens with what happens next. The star does not remain hidden. After weeks or months, the soot cloud, no longer gravitationally bound to the star, begins to drift away. It dissipates into the void, and just as suddenly as it vanished, the star snaps back to its original brightness, as if a switch has been flipped. There is no gradual return. It is an on-again, off-again relationship with the cosmos, entirely dictated by the spontaneous formation of carbon dust in its own sky. What internal thermostat, what atmospheric instability allows for such a precise and dramatic dimming mechanism? We are left watching these celestial ghosts, never knowing when the next great fade will begin. The chemistry of a star is its autobiography, written in the light it emits. Most stars tell a familiar story of hydrogen and helium with a faint sprinkle of heavier elements, but some supermassive stars are screaming a different story entirely, one that reads like pure science fiction. Their atmospheres are contaminated with bizarre and extreme abundances of specific elements. We see stars with surfaces glittering with far more mercury or platinum than should be possible, or others where phosphorus or certain rare earth elements are wildly overproduced. These strange metallicity signatures are not just minor anomalies, they are direct challenges to our fundamental models of how stars forge the elements of the universe, a process called nucleosynthesis. Deep within a star's core, nuclear fusion builds heavier elements step by step, like a cosmic assembly line. Hydrogen fuses into helium, helium into carbon, and so on up the periodic table. This process follows a predictable path, creating a predictable mix of elements that should be dredged up to the surface over the star's lifetime. But these peculiar stars have a recipe that is completely off-book. Their surfaces are coated with elements that should be buried deep in their cores, or with strange isotopes that require very specific and seemingly impossible conditions to form in such abundance. One leading theory points to a phenomenon known as radiative levitation. In the incredibly dense and radiation-soaked interior of a supermassive star, the sheer pressure of light can be enough to physically push certain types of atoms upward against the pull of gravity. It is as if the star's own brilliance acts as a cosmic filter, selectively lifting specific elements from the deep furnace and depositing them on the surface, creating a strange and unnatural-looking outer layer. Another possibility involves the star being born from the ashes of a previous, even more massive generation of stars, inheriting its bizarre chemistry from a primordial explosion we have yet to fully understand. These stars are not just oddities, they are living experiments, showing us that the cosmic forge operates in ways we are only beginning to glimpse. What other elemental secrets are these stellar chemists hiding, and what do their strange recipes tell us about the history of our galaxy? The ultimate expression of stellar inflation creates a star so vast it defies all sense of scale. We are speaking of hyper-inflated envelopes where a star swells to a size that pushes the very definition of what a star can be. The red supergiant Stephenson 218 is the reigning champion of this category, a leviathan whose dimensions are almost incomprehensible. If you were to place this star at the center of our own solar system, its outer surface would reach out and engulf the orbit of Saturn. Every planet from Mercury to Saturn would be orbiting deep within its incandescent atmosphere, vaporized into nothingness. This is not merely a large star, it is a stellar system unto itself, a volume of space so dominated by a single object that it contains over 10 billion times the space occupied by our Sun. How does a star achieve such a staggering size? The process begins near the end of its life. As a supermassive star exhausts the hydrogen fuel in its core, it begins to fuse heavier elements in shells around a collapsing heart. This new, more energetic fusion pushes outward with tremendous force, causing the star's outer layers to expand at a ferocious rate. The gravity at the surface of these hyper-inflated stars is incredibly weak, so tenuous that it barely holds onto its own atmosphere. A star like Stephenson 218 is less like a solid ball of fire and more like a cosmic cloud, a vast, diffuse sphere of superheated gas held together by the faintest of gravitational tethers. It is a structure perpetually on the verge of dissipating into the void, a temporary and fragile bubble of matter. The very existence of these giants challenges our theoretical models. There is a predicted upper limit to how large a star can become before its own radiation pressure overcomes gravity and it simply blows itself apart. Stars like Stephenson 218 appear to be dancing right on that razor's edge, testing the absolute boundaries of stability. They are the ultimate expression of stellar old age, cosmic balloons inflated to their theoretical maximum, destined for a final, spectacular collapse that will seed the galaxy with the elements forged in their impossibly vast interiors. How long can a structure so fragile and immense possibly last before the inevitable happens? This immense fragility finds its ultimate expression in one of the universe's most violent spectacles, a tidal disruption event. When a star drifts into the crushing gravity well of a supermassive black hole, it is subjected to forces so extreme they can shred a stellar body in a single catastrophic pass. For an ordinary star, this is a dramatic death, but when the victim is a supermassive star, the event becomes something far more complex and strange. The key is the difference in gravitational pull. The black hole's gravity is so intense that the side of the star closest to it feels a vastly stronger pull than the side farther away. This difference, the tidal force, stretches the star horizontally while compressing it vertically, pulling it apart like cosmic taffy. The star does not just explode, it is systematically unraveled. For a supermassive star, this process is drawn out and peculiarly productive. Its vast size means the tidal forces can begin their work while the star is still relatively far from the black hole's point of no return, the event horizon. The star is stretched into a long, thin stream of superheated gas, a process called spaghettification. This isn't the end of the story, it's the beginning of a brilliant and bizarre aftermath. The stream of stellar debris doesn't just vanish into the black hole. About half of the star's material is flung away into the darkness, while the other half forms a seething, frenzied accretion disk around the black hole. It is this disk that creates the true fireworks. As the gas spirals inward at a significant fraction of the speed of light, it is compressed and heated to temperatures of millions of degrees. The friction and magnetic fields within this maelstrom become so intense that the event can outshine every star in its host galaxy for months or even years, glowing brightly across the X-ray and ultraviolet spectrum. The presence of a supermassive star with its unique chemical composition and immense mass fuels a brighter, longer, and chemically richer event. The disruption pollutes the black hole's vicinity with a specific signature of heavy elements that were being forged in the star's core, a final stellar autopsy written in light. We are not just watching a star die, we are witnessing the birth of a temporary, ultra-bright engine powered by the corpse of a giant. What other secrets about stellar composition are revealed in the brilliant death scream of a star being fed to a black hole? The violence of a tidal disruption is a stark reminder of the power of spin, but a star's own rotation can be just as self-destructive. These stellar engines do not all turn at the same serene pace. Some whirl with such ferocious speed that they are perpetually on the verge of flying apart, while others spin with an almost imperceptible slowness that defies expectation. This strange spectrum of rotation rates is not a minor detail. It is a fundamental force that dictates a star's entire life and violent death. Picture a figure skater pulling their arms in to spin faster. Now imagine a star doing the same on a cosmic scale. As a supermassive star evolves and its core contracts, its rotation can accelerate to dizzying velocities. The centrifugal force at its equator becomes so powerful that it actively fights against gravity. These stars are not perfect spheres. They are flattened at the poles and bulging at the equator, distorted into oblate spheroids by their own incredible momentum. Matter at the equator is flung outward, held on by the thinnest of gravitational threads. In the most extreme cases, a star can reach its critical breakup velocity, where gravity can no longer hold it together. It begins to literally hurl its own surface material into space, not through radiation or wind, but through sheer rotational force. This creates a different kind of mass loss, a centrifugal slinging of matter that forms a decretion disk around the star, a glowing belt of its own shredded body. This rapid spin is a key ingredient for the most cataclysmic explosions, like gamma-ray bursts, where the star's rotational energy is channeled into those universe-lighting jets. But what about the other end of the spectrum? Why would a supermassive star rotate slowly? A sluggish spin is just as puzzling. In a binary system, tidal forces can act as a brake, synchronizing one star's rotation to its orbital period and dramatically slowing it down. A strong magnetic field can also act as an anchor, its lines acting like cosmic rains that drag through the stellar plasma and sap its rotational energy over time. This slow rotation has profound consequences. It weakens the star's magnetic dynamo, often resulting in a less intense but broader and more organized magnetic field. It also changes how the star sheds mass, leading to a more spherical and steady stellar wind instead of the focused, jet-like outflows of its fast-spinning cousins. The star's ultimate fate is rewritten by its spin. A fast-spinning star might collapse into a rapidly rotating neutron star or power a gamma-ray burst, while a slow spinner may produce a more conventional supernova. The speed at which a star turns is a hidden dial, setting its course for either a focused, jet-driven death or a spherical, explosive end. How can two stars born from the same cosmic cloud end up with such drastically different rhythms, and what does that tell us about the chaotic processes of stellar birth? Even the final act of a supermassive star is not a guaranteed performance. You might assume that a giant star's death is a singular, spectacular event, the supernova, a predictable final blaze of glory. The reality is far stranger. The deaths of these stellar behemoths are as diverse and bizarre as their lives, producing a catalogue of cosmic explosions that defy our simplest classifications. We see supernovae that behave like cosmic imposters, others that should not exist at all, and some that simply fail to appear, vanishing from the universe in a silent, dark collapse. Consider the type in supernova. The N stands for narrow, a clue to its most peculiar feature. When most stars explode, the blast wave slams into the surrounding interstellar medium, which is relatively empty. But a type in occurs when a supermassive star has already spent its final years shedding its outer layers in violent, erratic outbursts. The space around it is not empty, it is filled with a dense, pre-existing cocoon of its own ejected gas. When the star finally does explode, the supernova blast wave does not rush out into a void. It smashes directly into this dense, slow-moving shell of material. The collision is ferocious, and it produces a brilliant, long-lasting light show. The narrow emission lines in its spectrum come from this dense shell, which is being lit up and ionized by the intense flash of the explosion from within. It is a supernova interacting with its own recent past, a star exploding into the ghost of its former self. Then there is the Pair-instability supernova, a theoretical beast made real. This is not just an explosion, it is total annihilation. For the most massive stars, those born with masses between about 150 and 300 times that of our Sun, the core becomes so hot that it crosses a catastrophic threshold. The radiation inside becomes so energetic it spontaneously creates matter and antimatter pairs, as we discussed with pulsations. But in this case, there is no recovery. The loss of pressure is so sudden and complete that the entire core collapses at once, triggering a runaway thermonuclear fusion that no structural force can contain. The entire star is obliterated. Not a single remnant, no neutron star or black hole is left behind. Every bit of the star is vaporized and flung into space in one of the most powerful explosions possible in the modern universe. It is a fireball of pure elemental creation, forging and scattering vast amounts of heavy elements like radioactive nickel, which powers its incredible brightness for months. This is a star committing suicide so completely that it leaves no corpse. Perhaps the most unsettling death is the one we cannot see, the failed supernova. Astronomers have literally watched massive stars simply disappear. One day, a star is there, shining steadily. The next, it has faded into oblivion without the brilliant fireworks of a supernova. The leading theory is a direct collapse into a black hole. In this scenario, a supermassive star with a particularly immense core reaches the end of its life. It begins the final collapse, but something goes wrong with the explosion mechanism. The rebounding shock wave that should rip the star apart simply stalls and falters. It lacks the energy to overcome the immense gravitational pull of the collapsing core. Instead of exploding, the star's outer layers fall inward, down into the newly formed black hole. The star is swallowed by its own heart, its light snuffed out in a relative instant. There is no grand explosion, just a quiet dimming as the last of the photons escape before the event horizon seals shut. It is a funeral without a eulogy, a star skipping its own death ceremony and proceeding directly to a dark, silent grave. How many of these stellar giants have vanished from the cosmos without a trace, their deaths marked only by the sudden, permanent absence of their light? A star's heartbeat can reveal secrets hidden deep within its core. For most stars, this pulse is a simple, rhythmic expansion and contraction, a steady breathing in and out. But supermassive stars often exhibit something far more complex and alien, a phenomenon known as non-radial pulsation. Instead of the entire star swelling and shrinking symmetrically, different parts of its surface are moving in and out at the same time. Imagine the surface of a vast ocean where countless waves are crossing, interfering, and creating a chaotic, rippling pattern. That is the surface of a star undergoing non-radial pulsation. These are not simple pulses, they are a symphony of oscillation modes, each one a vibration rippling through the star's interior. Some modes are like sound waves traveling around the star's equator, while others dive deep toward the core and back out again. Each mode of vibration is sensitive to different conditions within the star, probing the density, temperature, and composition of its hidden layers. When astronomers observe the flickering light of one of these giants, they are essentially listening to its music. The complex pattern of brightening and dimming is a code that can be deciphered. By studying the specific frequencies of these oscillations, scientists can perform stellar seismology, a way of seeing inside a star by observing how it vibrates. It is like taking an ultrasound of a stellar giant. This reveals the internal structure in a way that simply observing its surface light cannot. A star might appear calm and steady to the naked eye, but its light curve tells a different story, one of internal turmoil and complex, overlapping waves of pressure and gravity. Why would a star vibrate in such a bizarre, multi-directional way? The sheer size and internal complexity of these supermassive stars create the perfect conditions for these exotic pulsations. Convection zones, where heat bubbles up from the interior, can act like giant pistons driving oscillations. Sharp changes in chemical composition between different layers can create boundaries that reflect these internal sound waves, setting up standing wave patterns. The rotation of the star further complicates the music, stretching and splitting the oscillation frequencies. The presence of a strong magnetic field can also channel and distort these vibrations, adding another layer of complexity to the stellar symphony. This is not just an academic curiosity. By decoding these vibrations, we have discovered that some supermassive stars have rapidly rotating cores hidden beneath seemingly calm outer layers. Others have mixed-up interiors where fusion products from the core have been churned throughout the star, dramatically altering its evolution and ultimate fate. Each strange pulse and flicker is a message, a direct transmission from the heart of a cosmic giant, telling us about the forces raging within. What other internal structures might be revealed as we learn to better listen to this celestial music? These feeding relationships can sometimes reverse in the most violent way possible. We find ourselves observing an unusual X-ray binary, a system where the cosmic tables have turned. Here, a supermassive star is not the predator but the prey, its outer layers being slowly consumed by a dead stellar companion. This companion is no ordinary star. It is the ultra-dense corpse of a long-dead star, a neutron star, or a black hole. The immense gravity of this compact object relentlessly pulls a stream of superheated gas from its massive partner. This gas does not fall directly in, instead, it spirals down into a searingly hot accretion disk, a vortex of plasma orbiting the dead star at nearly the speed of light. The friction and compression within this disk heat the material to temperatures of millions of degrees, causing it to glow with an intense, piercing light in the X-ray part of the spectrum. This is not a steady beacon, though. The X-ray output from these systems is wildly variable, flickering and flaring in bizarre, unpredictable patterns. Sometimes the flow of gas is smooth, producing a steady hum of X-rays. Other times, the disk becomes unstable, clumping and dumping vast quantities of matter onto the neutron star all at once, triggering a colossal X-ray flare that can outshine a million suns. In systems with a neutron star, its powerful magnetic field can act like a cosmic gatekeeper, funneling the incoming gas onto its magnetic poles. This creates incredibly hot spots that rotate in and out of our view, producing a regular, pulsing X-ray signal, a lighthouse beacon from the edge of a gravitational abyss. The most peculiar patterns arise when the compact object is a black hole. Here, the inner region of the accretion disk can undergo quasi-periodic oscillations, a rhythmic flickering that is almost, but not quite, a steady pulse. It is the sound of space-time itself vibrating near the event horizon, the last frantic churn of matter before it vanishes from our universe forever. These strange X-ray symphonies are more than just a cosmic light show. They are a direct probe into the most extreme gravitational environments we can observe, allowing us to study the properties of matter and the nature of gravity itself under conditions impossible to recreate on Earth. What other secrets about the fundamental laws of physics are being whispered to us from these violent, dueling stars? History can rewrite itself in light. When a supermassive star erupts or explodes, the flash of that cataclysm races outward in all directions at the speed of light. Most of that light travels directly to our telescopes, carrying the first news of the event. But some of it takes a detour, a longer, ghostly journey that allows us to literally re-observe the past. This is the mystery of light echoes. The phenomenon relies on vast, dark clouds of interstellar dust that float in the emptiness between stars. Think of these clouds not as solid objects, but as cosmic fog banks composed of trillions of microscopic silicate and carbon grains. When the initial flash from a stellar explosion slams into one of these distant dust clouds, it acts like a flashbulb in a dark room, illuminating the cloud from our perspective. We see the cloud suddenly glow, not with its own light, but with the reflected light of the ancient explosion. The incredible part is the timing, because the light taking the detour path has to travel farther to reach the dust and then farther still to bounce back to us. It arrives years, decades, or even centuries after the initial direct light from the event. It is a cosmic replay, a delayed broadcast of a stellar catastrophe. The most famous example comes from the year 1680, when a new star blazed into view in the constellation Cassiopeia. Astronomers, including the famed John Flamsteed, recorded the position of what we now know was a supernova, the violent death of a massive star. Then, in the 1980s, astronomers using powerful modern telescopes detected a faint, expanding shell of gas at that exact location, the remnant of that ancient explosion. But the real magic happened when they noticed faint, rippling rings of light appearing around the remnant. These were not part of the remnant itself. They were light echoes. The light from the 1680 supernova had finally reached a distant dust shell and was now reflecting back to Earth over 300 years after the star itself had died. By analyzing the spectrum of this echoed light, scientists could perform a forensic analysis on a 300-year-old explosion as if it had just happened. They could determine the type of supernova, its chemical composition, and the physics of the blast wave, all from an event witnessed by astronomers using primitive telescopes. This is not limited to supernova. Light echoes have been detected from the violent eruptions of luminous blue variables, allowing us to study their outburst cycles long after the star itself has calmed down or even met its final fate. Each echo is a message in a bottle, launched from a different point in a star's violent history, finally washing up on the shore of our present time. What other forgotten stellar dramas are still traveling through the void, waiting for a cosmic mirror to reveal their secrets to us? We are now listening to the universe with an entirely new sense, detecting the subtle ripples in space-time itself. These gravitational waves are often generated by the most violent events imaginable, and merging supermassive stars are among their most promising future sources. When two of these colossal giants are locked in a binary dance, their fate is a slow, cosmic spiral toward catastrophe. They orbit each other for millions of years, but as they do, they lose energy by radiating gravitational waves, invisible ripples that stretch and compress the fabric of the cosmos. This loss of energy causes their orbits to slowly decay, pulling them closer and closer together. The final act is one of unimaginable violence. When the two stars finally merge, they create a storm in space-time, a brief, furious burst of gravitational waves that carries the signature of their immense masses and final, frantic moments. Future gravitational wave detectors, like the Laser Interferometer Space Antenna, will be tuned specifically to catch the low-frequency rumble of these stellar collisions. This will open a window into the lives of supermassive stars that light alone can never provide. We will be able to weigh them with unprecedented accuracy, probe the structure of their internal layers, and test the very laws of gravity under the most extreme conditions. It is the ultimate autopsy of a stellar giant, reading the story of its death not from its light, but from the permanent wrinkles it left in the universe. What hidden properties of these stars will be revealed when we can finally feel their collisions across the void? The violence of a star's life is written in the space around it. Surrounding many supermassive stars are circumstellar environments of breathtaking complexity, chaotic realms of glowing gas and dust that defy simple explanation. These are not the serene, spherical halos you might picture. Instead, they are dynamic and often wildly asymmetrical structures, filled with colossal disks, screaming jets, and vast, misshapen nebulae that change before our eyes. The classic image of a star is a sphere, but the environment it carves for itself is anything but. We observe bizarre, pinwheel-shaped nebulae where spiral arms of dust are swept out by a hidden companion star. We see vast bipolar lobes that stretch for light years, looking like a cosmic hourglass. These shapes are the direct result of the star's own ferocious activity. Powerful magnetic fields can channel the star's wind into two opposing jets, carving out cavities in the surrounding interstellar medium and creating those distinct lobed structures. If the star is part of a binary system, the gravitational tug of war with its partner can whip the ejected material into those intricate spiral patterns. These are not static sculptures, they are live recordings of stellar forces in motion. Within these nebulae, we find strange clumps and knots of exceptionally dense gas. These are not random features, they are often the remnants of specific, violent outbursts from the star, like giant cannonballs of material fired into space during a luminous blue variable eruption. These clumps can be so dense that they shield molecules from the star's destructive ultraviolet radiation, allowing complex chemistry to occur within their protective cores, a surprising oasis in a stellar desert of radiation. The entire system can evolve with stunning speed. A jet might flicker on and off over mere decades, its direction wobbling as the star's magnetic field realigns. A dust cloud born from a single great eruption can expand and dissipate within a human lifetime, a fleeting monument to the star's instability. This forces us to see these stars not as isolated points of light, but as the turbulent hearts of vast, evolving ecosystems, each one a unique and transient work of art, sculpted by the invisible forces of gravity, magnetism, and raw stellar power. What other fleeting structures are we missing in the violent neighborhoods of these cosmic giants? The wind from a supermassive star should roar louder as the star burns brighter, but some of these giants whisper instead. This is the baffling case of anti-correlated winds, a behavior that turns our basic understanding of stellar mechanics upside down. Standard stellar wind theory is beautifully straightforward. The intense radiation from a luminous star pushes on the atoms in its outer atmosphere. This radiation pressure, as it is called, accelerates material away from the star, creating a powerful, continuous wind. The logic is simple: the brighter the star, the stronger the push, and the faster and denser that wind should be. It is a direct relationship, a fundamental rule written into countless textbooks. Yet, for a peculiar group of supermassive stars, this rule is broken. Astronomers observing these objects have witnessed a star's luminosity surge during an outburst, its brilliance increasing dramatically, only to see its stellar wind become weaker and thinner. The ferocious hurricane of particles inexplicably dwindles into a gentle breeze, even as the stellar furnace rages more intensely than ever. It is as if you turned a furnace to its maximum setting and felt the heat vanish from the room. How can more light result in less push? The answer may lie in the very structure of the wind itself. In a normal, bright star, the wind is driven by the absorption of the star's ultraviolet light by specific elements like iron in the atmosphere. This absorption gives the atoms a kick, propelling them outward. But in an incredibly luminous star, the radiation becomes so intense that it strips those key atoms completely. It rips away their electrons, leaving them ionized and transparent. Suddenly, the light passes right through them. The very mechanism that was supposed to drive the wind has been disabled by the star's own excessive power. The radiation has essentially shot its own accelerator. There is no longer anything for it to push against effectively. Another possibility involves the star's immense size. When a hyper-inflated supergiant brightens, its outer layers may expand so much that the gravity holding them becomes even weaker. This could allow the wind to escape more easily, but in a more diffuse, less energetic flow, like a slow, billowing cloud rather than a focused jet. The increased energy is spent on inflating the star's atmosphere to a more tenuous state, rather than on accelerating it. This bizarre anti-correlation forces us to see these stars not as simple engines, but as complex systems where a change in one part can trigger a counterintuitive reaction in another. It is a stellar paradox, a reminder that in the most extreme environments, the most logical rules can sometimes fail. What other fundamental relationships might break down when a star's power reaches its absolute limit? Even the wind from a supermassive star can tie itself into knots. As these colossal stars spin, their surfaces are not uniform. Different latitudes can rotate at slightly different speeds, and various surface features like giant magnetic spots or convective cells can create distinct pockets of hotter, more active plasma. Each of these regions blows its own version of the stellar wind, a stream of particles with its own unique speed and density. Because the star is rotating, these individual wind streams do not travel outward in straight, radial lines. Instead, they are flung out along curved, spiral paths, much like water droplets from a spinning garden sprinkler. Faster-moving wind streams inevitably catch up to the slower, denser streams that were ejected earlier from a different part of the star. When they collide, it is not a gentle merging. The faster wind plows into the slower one at supersonic speeds, creating a powerful shock front. In this violent collision zone, the gas is compressed, heated to extreme temperatures, and piled up into a dense, co-rotating interaction region. These are not random clumps, they are organized, spiral-shaped waves of dense material that rotate along with the star, constantly forming and reforming in the wind. From our distant viewpoint, this creates a rhythmic modulation in the star's observable properties. As one of these dense spiral arms rotates into our line of sight, it absorbs more of the star's ultraviolet light, causing a specific dip in its spectrum. When the arm rotates out of view, the wind appears clearer and the spectrum brightens. We see the star's wind pulsating in a regular, predictable cycle, a direct result of this internal traffic jam in its atmosphere. This phenomenon turns the stellar wind from a smooth, uniform flow into a structured, dynamic storm. The co-rotating interaction regions act as factories for complex molecules and dust grains, as the high density within the shock fronts provides the perfect conditions for atoms to collide and stick together. They also efficiently accelerate particles, creating localized hotspots of cosmic rays within the wind itself. The entire outflow is sculpted by the star's spin, a visible testament to how rotation imprints order onto even the most chaotic stellar processes. What other intricate patterns are woven into the gales of these spinning giants? This rhythmic pulse finds an even more intimate expression in the photometric heartbeat. Far from the chaotic flickering of a dying star, this is a precise, predictable signal born from the gravitational dance of two stellar giants locked in a close, elliptical orbit. As these stars swing around each other, their mutual gravity creates immense tidal forces, stretching each star into a football shape. The pull is strongest when the stars are at their closest point, a moment known as periastron. It is here that the heartbeat occurs. The gravitational squeeze at periastron is so powerful that it actually distorts the star's very structures, making them slightly larger and brighter for a brief period. This is not a change in their core fusion, but a physical, elastic response to an overwhelming force. As the stars then swing away from each other on their elongated paths, the tension relaxes, their shapes return to normal, and their light fades back to its standard brilliance. The entire system brightens and dims with the steady, reliable rhythm of a cosmic metronome, a direct result of this periodic gravitational stretching. The light curve this produces is astonishingly similar to an electrocardiogram of a human heart, with a sharp peak in brightness corresponding to the moment of closest approach, followed by a gradual decline. Each beat in the light is a direct measurement of the star's gravitational bond, a pulse that reveals their masses, their orbital distance, and even the internal structure of their gaseous bodies. How many of these stellar hearts are beating in the darkness, their rhythmic flashes telling a story of an intimate and powerful gravitational embrace? This internal churning can be so powerful it rewrites the star's very blueprint. Most stars live their lives like a layered cake, with hydrogen fusion in the outer core, then a shell of helium fusion, and progressively heavier elements like carbon and oxygen burning in deeper, more confined layers. This stratified structure is fundamental to our understanding of stellar evolution, dictating how a star will age and die. But for some supermassive stars, this classic model is completely wrong. They follow a path known as chemically homogeneous evolution, a process that requires one crucial ingredient, a spin so rapid it stirs the star into a uniform mixture. Imagine a cup of coffee where you've carefully poured in cream, creating distinct layers. Now, take a spoon and stir it with such ferocious speed that the cream and coffee become a single, uniform liquid. That is what happens inside these stars. Their immense rotational velocity creates powerful internal currents and instabilities that churn the entire stellar interior from the core to the surface. Fresh hydrogen from the outer regions is constantly dragged down into the furious heart of the star, while the helium ash produced by fusion is hauled upward and distributed throughout the body. The star does not develop the usual onion-like layers. Instead, it remains chemically uniform, a nearly perfect mix of hydrogen and helium from its center to its edge. This constant replenishment of fuel in the core allows the star to burn brighter and longer than a stratified star of the same mass. It never becomes a red supergiant because it never develops the inert, layered core that leads to the dramatic puffing up of its outer envelope. Instead, it stays exceptionally hot and blue throughout its life. This bizarre life path leads to an equally bizarre death because the star remains compact, hot, and rapidly spinning until the very end. It is a prime candidate to produce a long-duration gamma ray burst when its core finally collapses. That uniform composition and ferocious spin are the perfect recipe for forging the ultra-relativistic jets that characterize those universe-scale explosions. A star that lived its entire life as a mixed blue giant is perfectly prepped to die in the most violent flash we can observe. How many of history's most brilliant cosmic explosions were born from stars that defied the layered structure we thought was universal? The light from a star is its unique fingerprint, a spectrum of colors that reveals its deepest secrets. But for some supermassive stars, this fingerprint is constantly shifting, a chaotic dance of spectral lines that flicker and change without warning. These are not the clean, stable lines of a calm star. They are the frantic, unpredictable signatures of an atmosphere in utter turmoil. In the spectrum of a normal star, dark absorption lines appear at specific wavelengths, created as elements in its atmosphere soak up light from the hotter layers below. These lines are like a steady, unchanging barcode. For these peculiar giants, however, that barcode becomes a blur of motion. Lines suddenly vanish, only to reappear moments later. Others split into multiple components or brighten into emission, as if the star itself is screaming light at specific colors. This strange spectral line variability is a direct window into a storm we cannot see. One of the primary culprits is the sheer violence of the star's own churning atmosphere. Massive convection cells, larger than our entire solar system, boil up from the interior, carrying vast amounts of heat to the surface. As these titanic bubbles of plasma rise and fall, they create localized regions of different temperature and density. When a hot, rising bubble moves into our line of sight, it can alter the ionization state of the atoms, causing their spectral signature to weaken or disappear entirely. It is like watching a star covered in colossal, bubbling cauldrons, each one momentarily rewriting the chemical message we receive. Another source of this chaos is the presence of colossal magnetic spots. These are not like the relatively small sunspots on our sun. They are vast, tempestuous regions where magnetic field lines burst through the stellar surface, suppressing convection and creating areas that are significantly cooler or hotter than their surroundings. As the star rotates, these spots march in and out of view, each one imprinting its own distinct spectral signature onto the star's overall light. The passing of a massive, cool spot might cause the absorption lines of certain elements to dramatically deepen, while a raging hotspot could create a temporary, brilliant emission line. The variability is a direct map of this magnetic fury playing out across the star's surface. Perhaps the most tantalizing explanation for certain highly specific patterns is the gravitational influence of an unseen companion. A closely orbiting black hole or neutron star, invisible to our telescopes, could be gravitationally tugging on the supermassive star, distorting its shape and stirring its atmosphere in a rhythmic yet complex pattern. The spectral lines would shift back and forth as the star is pulled first toward us and then away, a telltale sign of an invisible dance partner. But in many cases, the changes are too erratic, too violent to be explained by a simple orbital motion. They point to something more fundamental, a deep-seated instability in the star's very nature. Each flickering line is a message, a real-time report from a front line of stellar physics where the rules are being written and rewritten in a storm of incandescent gas. What other invisible dramas are being encoded in the ever-shifting light of these celestial giants? Even in the quiet retirement communities of the cosmos, rule breakers emerge. Globular clusters are vast, spherical collections of hundreds of thousands of stars, all born from the same primordial cloud at nearly the same time. They are the universe's senior centers, filled with ancient, aging stars, all quietly burning through their final reserves of fuel. Their collective light should be a uniform, cool red. Yet, scattered defiantly among these elderly suns, we find blazing blue rebels. These are blue stragglers, stars that appear far too hot, too massive, and too young to exist in such an ancient neighborhood. It is like walking into a room of 90-year-olds and finding a vibrant, muscular 20-year-old. Their very presence is a paradox that defies the most basic principle of stellar clusters. How can a star be younger than the cluster that contains it? The answer lies not in extended youth, but in stellar theft and violence. The most likely explanation is cosmic cannibalism in a crowded environment. In the dense core of a globular cluster, stars are packed so tightly that close encounters and even direct collisions are not rare events, but expected outcomes. Two aging, lower-mass stars in a binary system can be driven to merge. Their combined hydrogen fuel and mass create a single, new, hotter, and more massive star, effectively resetting its evolutionary clock. This stellar Frankenstein's monster shines with a brilliant blue light that makes it look deceptively young. Another pathway is mass transfer, where one star in a close binary pair siphons the outer layers from its companion. This fresh infusion of hydrogen rejuvenates the thief, allowing it to burn brighter and bluer, while its donor is left as a stripped-down, withered core. These blue stragglers are not truly young, they are imposters, their youthful appearance built from the cannibalized remains of their elderly neighbors. They are a testament to the dynamic and often violent social lives of stars in crowded spaces, proving that even in old age, a cosmic merger can create a spectacular second act. What other cosmic deceptions are hiding within these ancient stellar cities? This strange chemistry can sometimes cloak a star in a signature we cannot yet decode. Surrounding certain supermassive stars, astronomers detect a persistent and perplexing glow in the infrared part of the spectrum. It is not the clean, predictable signature of normal stardust. Instead, it is a messy, complex emission, a set of unidentified infrared bands that act like a cosmic fingerprint for a substance we have not yet identified. These are not random signals, they appear at specific wavelengths, implying a very specific source, yet that source remains one of the great unsolved puzzles in astrochemistry. The leading suspects are complex organic molecules, vast structures of carbon and hydrogen known as polycyclic aromatic hydrocarbons. Think of them as microscopic flakes of soot, not random char, but organized, ring-like molecules that vibrate at precise frequencies when warmed by the star's light. These vibrations produce the exact kind of broad infrared emission we observe. The mystery is not just their presence, but their staggering abundance and resilience. How can such delicate carbon-based structures survive the hurricane of ultraviolet radiation blasting from a supermassive star? That intense light should tear these molecules apart in an instant. Their continued existence suggests they are forming in shielded environments, perhaps deep within the dense clumps and knots of the star's own ejected nebulae, where they are protected long enough to grow into these complex forms. Another, more exotic possibility involves entirely new types of carbonaceous dust grains, perhaps with unusual crystalline structures that produce these unique spectral features. These unidentified emissions are more than just a curiosity, they are a direct challenge. They hint at a rich and complex chemistry occurring in the violent outskirts of these stellar giants, a chemical factory producing materials we do not fully understand. If these are complex organic molecules, their prevalence around supermassive stars suggests these cosmic engines could be seeding vast regions of space with the prebiotic building blocks for life, all while shrouded in a spectral mystery. What other molecular secrets are hidden within this unexplained infrared glow, and what could they tell us about the origins of complexity in the cosmos? The ultimate cosmic disappearing act may not be an explosion, but a silence. We have already seen how some massive stars appear to simply vanish. The final, and perhaps most unsettling, enigma is the direct collapse to a black hole, a death so quiet it leaves almost no trace. This is not a star going out with a bang, but with a whimper that is nearly impossible to hear. The theory is as elegant as it is terrifying. For a supermassive star with a particularly immense core of iron, the final moments are a delicate balance. As the core collapses under its own weight, a rebound shockwave normally forms, ripping the star apart in a supernova. But if the core is too massive, this shockwave loses its fight. The sheer gravitational pull of the collapsing material is so overwhelming that the rebounding shock stalls and falters, lacking the energy to push back. Instead of exploding outward, the star's entire outer envelope simply falls inward, down into the newborn black hole. The light from the star's surface is not blasted into space, but is snuffed out as the event horizon forms and seals. From our distant vantage point, a star that shone for millions of years simply fades from view over a matter of months, vanishing into a permanent darkness. The evidence for this is still circumstantial but compelling. Astronomers have pointed telescopes at known massive stars, only to find them gone in later observations without any record of a supernova. The most famous case is the star N694 in the galaxy M101. It was a brilliant supergiant monitored for years, then it disappeared. Searches for a supernova remnant came up empty, leaving a profound silence where a giant once roared. This silent death has profound implications. It suggests that a significant number of the universe's most massive stars are ending their lives in this dark, secretive manner, leaving behind black holes without the brilliant funeral pyre of a supernova. It means our census of stellar deaths is incomplete, and that the cosmos may be far more efficient at creating black holes than we ever realized. How many of the dark shadows in our galaxy were once brilliant giants that chose to exit the universe not with a final, defiant scream, but with a silent, final bow? These 30 cosmic phenomena are not distant curiosities. They are the fundamental, chaotic processes that govern the universe's most powerful engines. From stars that tear off their own skin to giants that vanish without a trace, each behavior reveals a universe far stranger and more dynamic than we ever imagined. These stellar giants are not just breaking the rules, they are actively rewriting them, forcing us to question our most basic assumptions about matter, energy, and the very fabric of space-time. Every flicker of light, every unexplained dimming, and every silent collapse is a direct challenge, pushing the entire field of astrophysics toward new and revolutionary discoveries. We have journeyed through a gallery of cosmic extremes, but the exploration is far from over. Now we turn the question to you. Which of these bizarre stellar behaviors did you find the most astonishing? Was it the star that fakes its own death, the one that spins itself into a uniform mixture, or the silent, dark collapse that leaves no trace? Share your thoughts in the comments below, and let's continue unraveling the universe's greatest mystery.